In this video, we're going to derive the formula for calculating complex roots based on De Moivre's theorem. But in order for you to appreciate that, we're going to start with some basics of trigonometry. So consider this triangle here. Imagine that, so there's a sketch of an isosceles triangle. So we know that if it's an isosceles triangle, it means each of the interior angles is going to be 60 degrees. So we're just going to focus on this one. If that is 60 degrees, if we split this in the middle, so that is going to be 90 degrees. That means this side is going to be 1. Then using Pythagoras, it means we can write that h squared plus 1 squared must be equal to 2 squared. So that means h squared is going to be 4 minus 1. So h is going to be square root 3. So from that, it means we can write the sine and cosine of 60. So it means, for instance, sine 60 is going to be opposite over hypotenuse. So there is the root 3 over 2. And cosine 60 is going to be 1/2. All right, now, so that's good enough. What we're going to do now is we're going to take just this half of the triangle and superimpose it on the complex plane. Okay, so this is now our complex plane. This is the real axis. This is the imaginary axis. So what we're going to do is we are just going to take that triangle and plant it here. Okay, so this is 1, like it is there, and that is square root 3. Okay, so this angle is going to be 60 degrees. The radial distance is going to be 2. So this complex number is just going to be 1 plus I root 3. 1 being the x coordinate, root 3 being the y coordinate. However, because we know the argument and the radial distance, we can write this complex number in polar. It's going to be 2 cis 60 degrees. Okay, so we're going to get back to these in a moment. Let's just talk about the angle. This angle here is 60 degrees if we stop at the terminal side immediately. However, what we can do is if we've got time and energy, we can start off here, go round once, and then come back. In which case, that angle is now going to be 420 degrees. 420 being 60 plus 360. If we've got even more time and energy, we can go around once and then stop at the second goal. In that case, that angle is going to be 780. Or alternatively, instead of going in the counterclockwise direction, we could go in the clockwise direction. This time, this angle is going to be negative 300. This is barely visible. Negative 300 degrees. We could do this. We could rotate once and then stop later. So we're going to have this whole lot of angles, all of which are such that you stop at this terminal side. These angles are called coterminal angles. Okay, so you have got 60 then you have got 60 plus 360. Then you have got 780, and then you can add another rotation. Then this side you have got negative 300. The next one is going to be negative. The next one is going to be negative 660, and then again you can keep going. What's going to happen? So these angles are called coterminal angles. So these are coterminal angles of 60 because they share the same terminal side as the angle 60. Coterminal angles of 60 degrees. Now, we just said sine 60 is root 3 on 2, cosine 60 is 1/2. The sine and cosine of each and every one of these is going to be the same as that of 60, which means the cosine of 420 is 1/2, cosine of 720 is 1/2, cosine of negative 300 is 1/2. So they all have the same trigonometric ratios. Okay, so coterminal angles have identical trigonometric ratios, okay, or equal trigonometric ratios. So let's just try out a few of these. So let's try cosine 420, and you can see it's 1/2. Cosine negative 300, negative 300 is 1/2, etc. So they all share the same trigonometric ratios. Now so there's an infinite of a number of them. So what we can do is to produce these, we can simply write 60. Let me write this here. You can simply write 60 plus 360k, where k is an integer. So if k is 0, then this thing is giving us 60. If k is 1, it's giving us 420. If k is 2, giving us 780. If k is negative 1, it's giving us this one. K is negative 2, it's giving us this one. So this is going to give us an infinite number of coterminal angles of 60. Now, in terms of going back to our complex number now, I've just said that 1 plus I root 3 is 2 times CIS of 60. However, if you, instead of 60, if you use 420, for instance, we are still going to have exactly the same complex number. So even though this is now a different angle, because cosine 420 is 1/2 and sine 420 is root 3 on 2. So if you remove brackets, we are back to this complex number. However, even 780 is going to be the same complex number. Negative 300 is going to be the same complex number. Well, what is this saying? This is saying the number 1 plus I root 3, which is 2 CIS 60, we can in fact write it as 2 CIS 60 plus K, let me put the K, plus 360K. So if we add multiples 360, we're still going to have the same complex number as this one. Okay, because all these numbers, all these angles are coterminal, and so they give the same sine and cosine. Now, in general, you're going to remember that the complex number, we can write it in this form or this abridged version. This is going to be the same as theta plus 360k. So that's what we can do in general. Or if we are working in radians, so this is going to be theta plus 2 pi k, where k is an integer. Okay, now we're going to combine this with De Moivre's theorem. So remember, for De Moivre's theorem, we said z to the power n, which is equal to r cis theta to the power n, is r to the power n cis n theta. So we raise the r to the power n, and we multiply the argument by n. So now what we're going to do is we're going to take the power to be a fraction. Okay, so for roots, we are going to take the power to be 1 over m, where m is an integer. So z to the power 1 over m is going to be equal to r cis theta plus 360k. Remember, we said this is exactly the same as that. Okay, then we are going to raise this to the power 1 over m. So similarly, r will be to the power 1 over m, and then we multiply 1 over m into the argument according to De Moivre's. So this is going to be cis theta plus 360 degrees times k all over m. And so this thing is going to give us a formula for finding the mth roots of z. Okay, so this is going to give us the formula for finding the mth root of z, which is the formula for calculating the mth roots of z. Now notice that there are always going to be mth roots of z. So here k, we can vary from 0, 1, 2 all to the m minus 1. But we're going to work through some examples in the next video. What we wanted to do right now is just to introduce this formula here, which is based on the fact that cis theta is the same as cis theta plus 360k, and so you combine this with the De Moivre's theorem, then you get this formula here. So how can you use it to find roots of z? We're going to do that in the next video. Okay, Thank you for visiting the channel. Thank you for watching the video. Hopefully it helps you some way. Please do not forget to subscribe to our channel, and if you've got any questions, you can post them in the comments section.